Hello, and welcome to our conversation about gravity, the constant force in your life. So the first question that I want to ask you is actually, why do we fall down? Well, the answer to why do we fall down is, of course, gravity. Now, I'd like to say at this point, no bears were harmed in the making of this PowerPoint. This is actually a situation where the bear was stuck in the tree and they put the little airbag so the bear could fall down, probably when he was passed out with a tranquilizer, but that's not important. So we know that the bear is going to fall down, he's going to hit the cushion and bounce up and then fall back down, right? Why does he do that? Gravity. Okay, so what is gravity? Gravity is that force that large bodies exert on near objects. Okay, so if you want to think about something like the Earth, it's going to have this huge gravitational field that will pull everything towards its center, and big bodies will pull each other, right? And so we'll talk about that more in just a second. But first, I want to talk about who studied all this. It was Newton, right? It's Newton that first really identifies the force of gravity and how it works. And we start with this conversation about falling objects. As we know, the story is about Newton sitting under his apple tree. He sees the apple fall and he starts thinking, well, I know that forces are required to move stuff. So what just happened? And it turns out that it is the force of gravity. And so there's this conversation about there's an invisible force that causes everything to move to the center of the Earth. Now, Newton actually knew that that was a little bit odd sounding because invisible stuff doesn't do things like that. I mean, wind does, right? But wind is actually stuff. And you can prove that air has mass. But gravity doesn't have mass, right? There's nothing actually pushing or pulling or anything when you have something falling. So Newton was able to accurately describe mathematically what is happening, but he wasn't really sure of the mechanism that was causing it to happen. But he did two really important things. He was able to describe how objects fall, right, how that works, and he was able to describe how gravitational fields interact, right, how large bodies interact with each other, and the kinds of effects they have on each other, right? So, as we're talking about gravity, the first thing that we really need to do is learn our vocabulary. So we already know that F of g is the force of gravity. Little g, we've talked a little bit about, because we keep wanting to put little g. Little g is a thing, and I told you it was a thing. It's the acceleration due to gravity, which is something that we will be talking about soon, okay? Big G is something we also see, and in the case of a subscript, it means gravity. But when you see big G by itself, it is also a thing, and it is the universal gravitation constant. So some relationships aren't direct, and they need another number in them that is a constant, right? So if you had like y equals 2x, right, you've got the 2 there, okay? So lots of relationships in nature have that kind of a sort of key that unlocks how to describe that. G happens to be one of those. It is the same number all of the time. It is the universal gravitation constant, and it is required to accurately calculate the force of gravity between two masses. So in this case, right, you've got the Earth and you've got the Moon, and they will act on each other. And so there's a force of attraction between the two of them, and it is based on how far away they are from each other. So universal gravitation is based on the size of the two objects that are interacting and the distance that they are apart. Now, this is an equation that you do not have to know. I want you to understand this idea that these two bodies will interact with each other and you'll have a force that's applied between them, just like there's a force applied between the Earth and you. It's just this is on a bigger scale. And so I want you to understand that concept, but you don't need to know this equation, but I did want to show it to you because this is the equation. So why would you care about universal gravitation? Well, it turns out that this relationship between these really large bodies, so we've got two situations. We've got the situation where you've got one body and a lot of stuff on that body, like us on Earth, like things on Earth, and then you have two big bodies interacting with each other, okay? Why do you care about the two bodies interacting with each other is because it is responsible for all sorts of fun things. all the great things that we get from orbiting around the sun, all the great things that we get from the moon orbiting around us. And you might be asking yourself, other than a beautiful night sky, what does the moon orbiting around us do for us? Well, it creates tides. Yay! So how does that work? First of all, it's really the moon that we're concerned with. The sun does impact tides. I liked this picture because it had all the good words on it, but really we want to be thinking about the moon, and so this picture has the moon on it. But the large bodies around us will pull, right, on us, right, here on Earth, this whole system that is the Earth. So the moon and sun will pull on the giant mass that is the ocean. And the part of the ocean that's closest to us, remember, that's based on the radius between the two, okay? And so this is closer, it's going to pull more, because if they're closer together, there's going to be a larger force. So they're going to pull more. So we get this gravity bulge, and this is where a high tide is. And then the Earth has, a distance too. And so it's going to be pulled on a little bit, not as much as this closer water is going to be pulled on, okay? And then the water over here is not pulled on very much at all. And so the Earth is actually pulling away from the water on the opposite side of the moon. And so you get another bulge. So over here, you get a bulge because of gravity. Here you get the moon pulling that is the Earth. You get the Earth pulling just a little bit. And then over here, you don't have a pull. So there's kind of the gap where the Earth is pulling away from the water, called the inertia budge, because the ocean has inertia. Now, because these are bulging, it's water, it flows, that's going to leave low areas perpendicular to the line of the moon, and so, or to the plane that we're on for those tides. So these are going to be the low tides, right? And then where the water's being pulled by the moon and then the Earth away from the water, that's going to be the high tide. And then the sun will also affect that. When the sun and the moon are actually kind of aligned, pulling on the same side, those are the highest tides of the year and the lowest tides of the year, right? Because it pulls a little bit more. Now, this is super exciting, right? We really like tides. They're very helpful. We can have a whole conversation about why tides are awesome later on if you want to. But something else happens that's really exciting as well. And that is that the moon doesn't just pull on the water. When it pulls on the Earth, because remember I told you it's going to pull the Earth away from the water on the other side. When it does that, it pulls on one side of the Earth more than it pulls on the other side, which creates this cute little bulge called the tidal bulge. So the Earth isn't perfectly spherical. It's actually squished. It's actually a little bit oval, in line with that pull of the moon. But the Earth moves and the moon moves, and so that bulge moves. And if you think about when you take a paperclip and you bend it back and forth a lot, it starts to heat up. Well, this matter constantly also heats up, and that gives that little that little heat boost gives us a little bit more added climatic stability. And that's a really important thing. And the Earth is a special place based on its location in the solar system. But it's also really special because we do have things like tides, and we have that little Earth bulge that gives us the heat boost. And all of that mixes together to make us have a climate that is able to support life. And so that's a really good thing. And that's another reason that we are having this conversation, even though we probably will not be calculating this. I do want you to understand the concept behind it. Okay, so let's go back to this idea of what is gravity. So Newton didn't really know what the invisible thing, the mechanism that was causing gravity. Okay, he was able to define the forces that were in play and accurately describe those, but he didn't really know what it was. But it turns out that gravity isn't some invisible thing. It's actually space. And we can't see space. Now, some would argue, like, well, we can't see air either, but it's a thing. Air is actually matter. Space is its own thing. Okay, so you have matter, and you have space, and you have energy, right? Space does its own thing, and we don't perceive space. We are able to perceive the effects of the curvature of space, and that would be gravity. But any body actually distorts space a little bit, but large bodies do it in a way that affects the actual travel of stuff out in space, okay? Well, and here too. So the example would, of course, be like moons and stuff, anything orbiting. But when something is in orbit, really what it's doing is it's just traveling in what it thinks is a straight line, because the actual path that it's traveling on is curved. So when we put a satellite up into orbit, we throw it really hard so that it arcs, and when it does that, it just continues to travel because there's no friction. It doesn't need a force. It travels at a constant velocity, inertia, right? So it's going to travel at that constant velocity just around this curved path, around whatever this large body is. And it's what the moon does around us. It's what the Earth does around the sun. If you have questions on this, ask me in class. I can explain it maybe better when we're in person. But that's basically what's happening. So what that means is you actually have a little bit of gravity too. It's so tiny that we can't measure it, but we could calculate it. That would be pretty exciting. It would have a huge negative exponent, but that's all right. But you do have a little bit. But really the effects are only going to be seen if you have something that is massive, like the moon or the Earth, or bigger, like the sun. So who figured this out? Einstein. So he was the person who actually figured out what was going on and what was the mechanism. And so Newton's description is correct, but it's Einstein that actually defines what's causing gravity. So in this conversation, we have talked about the force of gravity, right, is always downwards towards the center of a massive body. That when we talk about the force of gravity, we are talking about this pull constantly, whether it is within a single body system, so like the stuff on the Earth, or between two bodies, right, which is described by the law of universal gravitation, like the Earth and the moon, or the Earth and the sun, right? And we know that those things affect stuff in the system. So if you have two bodies, right, the moon, the gravitational pull of the moon on the Earth is what causes tides and the tidal bulge, and that we know that Newton described these mathematically, which is the way we're going to talk about them, but it's actually Einstein that figured out that it's really the curvature of space that causes that, and even things in space that curve are actually still following Newton's law of inertia. There's no force acting on them. They're just following the path of space, okay? And so that's why in space we can get things to curve. On the Earth, we're going to need forces to make that happen. Okay, so that is our conversation about gravity. If you have any questions, I hope that you've written them down. Don't forget to take your video notes quiz. And the secret word is apple, right? That's our Newton thing. Apple. Secret word is apple. All right, I will see you guys next time. Thanks for listening.